Yeah, so I think we can start our class for the day. I hope my voice is audible to you and my screen is also visible to you.
Yes, sir.
Okay. So in the last lecture, I think talked about the carbon nanotube interconnection. Also, we talked about the network on chip for future interconnection. Then we talked about the switching threshold of the CMOS inverter. And then we also talked about how to determine this noise margin from the inverter gain, CMOS inverter's gain. And then we also found that one can shift the switching threshold either towards VDD or towards ground. Okay. Now, this switching threshold, just I want to add few more things here. That this switching threshold is a point where my output is equal to input, right? So CMOS inverter's output is equal to input, right? So this is my switching threshold point, right? Now, if I want to shift the switching threshold up, that is towards VDD, right? So that means this VTC also would be modified, right? So VTC also should modify to support this movement. That is, we want to move the VTC towards VDD, right? So that means we want currently my switching threshold, that is VM, is located here, and let's say I want to move my switching threshold VM towards VDD. That is maybe at this point, yeah, somewhere here. Maybe let's say 1.5 we want, okay, here at this point. So that means my VTC also should be modified. So for the new transistor, when I will increase the PMOS width, then maybe you will see this VTC also gets modified. And now maybe you will see that the switching threshold lies here at this point. Okay. Similarly, if you want to shift the switching threshold towards ground, so that means my VTC again has to be modified. Okay. So the VTC, the modified VTC may look somewhat like this. Okay. So that means that if I am increasing the width of my PMOS to move the switching threshold towards VDD, so my VTC will shift towards the right. Okay. And if I am trying to move my switching threshold VM towards ground, okay, so that means my VTC will move towards the left. Yeah. So that means I am trying to make my NMOS strong, that is NMOS wide, right? So WP by WN ratio is now smaller in this case when my VTC is shifted towards the left. That is when my VM is brought down towards the ground. Similarly, when my VM is brought up towards the VDD, then my VTC is shifted towards the right, and my PMOS width has to be increased for this effect. Okay. Then we also discussed these 2 points, right? That is where the slopes of these lines which you draw here on these two. So the slopes of these lines are negative, right? So -1. We said that slope of these tangents, that is dV out by dV in, at these 2 points is negative. Okay. And here at this point, V naught is equal to V in, okay, or the slope of this line. Okay, this line, that is this line which you are seeing here. So the slope of this line is 45 degree. Okay. So in fact, this can be found easily from the VTC by simply writing the equation of the straight line, right? So this is a straight line actually, which is passing through the origin. So if I try to write the equation of straight line, so that would be y is equal to mx plus c, right? So y is V out here, right? So by y is mx plus c, if I utilize, y is mx plus c. So y is here V out, so I say V out is, and m is this tan 45, right? So M is 45. So I say Y, that is V out is tan 45 degree multiplied by V in. Okay. Or this comes out to be as V out is equal to V in, this point. Okay. Now similarly, the slopes of these two regions can be defined. Okay. And the gains at these 2 points. So here if I try to plot the slope, in fact I'm writing it as gain here, but actually it is the slope of these two lines, I mean the entire VTC, right? The slope of the entire VTC is presented here. So we call it as gain, and you will notice here these 2 points, that is this one where gain is -1 and this one. So these two appear here, these 2 points. So these two, at these 2 points the gain is -1. Okay. Now this can be also found from the same analysis. By extending the same straight line equation analysis, one can find out these two things. Okay, so let us try to find out by considering, let us first of all make a straight line over here. Okay, so let us draw a 45-degree line first of all here, maybe at this point. Okay, so let us try to draw it. So let us say this is my tangent to the point of interest. Okay, so this is my tangent to the point of interest. Yeah, this was the point here. So let's say this is the tangent to that point of interest. Okay, now let us extend this axis also, the x-axis. So let us try to extend the x-axis here, this one. So that means this is cutting the x-axis here at this point. So we can decide the coordinates of these 2 points. That is coordinate of this point and the coordinate of this point. Right. So coordinate of this point can also be decided by again some approximations. So let us try to make some approximations. So this is y coordinate for this point, and maybe let us say this one would be my x coordinate. Okay, so I'll shift it a little bit here. Yeah, that means the coordinate of this would be somewhere around maybe this is, let's say, 1.1 comma and 2.25, let us say, right? So let us write it. Let us write the coordinates. So the coordinates are, for this point, it is 1.1, let's say, comma, and this is 2.2, let's say, 2.2. So again, we are making approximation, so the result may not be that much accurate, but yes, it will give us a hint of how these things are found. So let us say that the coordinates are now, for this point is 1.1 comma 2.2 x and y. Similarly for this, the coordinates could be set as maybe, let's say this is 3 comma x is 3, x is 3 and y is 0. So let us write here the coordinate of this point as 3 comma 0. Okay. So I'll write 3 comma 0. Okay. Okay. Now let us write the equation of this straight line, which is passing through these 2 points, right? So if you remember, the equation of line which is passing through 2 lines is given by, maybe I'll write here. So the equation of straight line can be given by, maybe on the next screen, let us take another screen here. So the equation of the straight line passing 2 lines can be given by y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. So if you remember class 10th mathematics, we used to use this equation to write the equation of straight line which is passing through 2 points. Okay, so x1 y1 is known to us. So x1 y1, for example, let us say x1 y1 is 3 0, right? So let's say my x1 y1 is 3 0, and similarly my x2 y2. So these are 1.1 and 2.2, right? So let me write 1.1 and 2.2. So 1.1 and 2.2. So these are x2, y2, right? So the coordinates. Now you use these coordinates here, and this term, that is this one, y2 minus y1 by x2 minus x1. So this is actually the slope of this line, right? So maybe we are more interested to find the slope, that is this point, right? So y minus, so that becomes y minus y1 is 0. So let's say y only. So y is y2 minus y1. So y2 is 2.2 minus 0, that is 2.2, divided by, we have x2 minus x1. So x2 is 1.1, this one is 3, 1.1 minus 3. Okay, so that means 1.9 and minus 1.9. Okay, multiply by x minus x1, and x1 is again 3. So we are interested in finding the slope which is represented by this term. So 2.2 by 1.9. Okay. So let us, the 2.2 by 1.9 we had. So let us take a calculator over here, calculator. And we say 2.2 divided by 1.9. So that is equal to 1.15, and this is minus 1.15, right? Now take, this is minus 1.15. So I say, let's make a sign also here, minus 1.15, and now let's take tan inverse. So tan inverse of this, so this is somewhere around minus 49 degree. Okay, so this is somewhere around minus 49 degree. And remember, the slope at these 2 points is minus 1, yeah? So minus 1 means minus 45 degree. That means this slope is, so this slope is minus 45 degree. So this is 45 degree, this one, and this is minus 45 degree. So that is why dV by d out is coming minus 1 over here. Okay, but in our calculations, what we are getting minus 49 degree. Okay, because we made everything approximate, right? We considered everything approximate. So we are getting minus 49 point something, that is 1.57, minus 1.157 we are getting. So here it's minus 1. Okay, because we made the approximations, right? So if you do a more careful analysis, you will find exact minus 1 or minus 45 degrees slope. So similarly, this minus 45 degree thing can be obtained here also, minus 1, that is slope is minus 1. So this can also be verified using the same. Okay, now similarly the gain at this point Vm, okay, the gain of, or the slope of this line which is touching this Vm. Okay, so maybe let me draw once again a line which goes through Vm, the slope, a tangent. So if I draw a tangent through, this slope, so that may look somewhat like this, maybe not like this. Maybe I'll bring it a little bit here. Yeah, somewhat like this, right? This tangent. Or maybe let me extend it a little bit. This one, right? So at Vm, you are seeing gain of somewhere around minus 17 here. You see that this is Vm, that is 1.25 volts. So at 1.25, you are seeing gain of, or dV by d out, that is slope is minus 17. Okay. So slope is minus 17. So at Vm, so the same slope can be found here, right? From this, the same analysis. That is, you mark the coordinates at this point Vm. So coordinates are 1.25 and 1.25 here. and at this point also you mark a coordinate. So let us mark another coordinate using the same way. So for this VM, that is this point, that is switching threshold, I have the coordinates as 1.25, 1.25. Let me make it a little bit small. Right. So at this switching threshold VM, the coordinates are, I mean, this point, we are considered about this point now, and we are also concerned about this point where this tangent is touching. Okay, so the coordinates of these 2 points, this is 1.25 and 1.25, and this one. So y is 0, but x is maybe, let's say it's somewhere around 1.3, right? So 1.3 comma 0. So let's write the coordinate as 1.3 comma 0 for this point, right? So I'll write it over here, 1.3 comma 0. Okay, so we got 2 points, and we'll apply the same concept here, that is equation of straight line, which is connecting 2 points, right? So 2 points are 1.25, 1.25 and 1.3 comma 0. So I'll go back again to this, maybe here itself we can calculate. So let us calculate it here. So I say y minus y1, that is, let's say this is x1, y1. Okay, so y minus 0 is, that means y, this is equal to y2 minus y1. So this is y2 1.25 minus 0. So 1.25 upon x2 minus x1. Okay, so this is x2 1.25 minus 1.3. So this is 1.25 minus 1.3 is 0.5 minus 1 minus 0.5 multiplied by, so x is v in minus, and this y is v out. So let us write v out here. Okay. V in minus x1. x1 is again 1.25. So since we are interested in this term, which is the slope, so 1.25 by minus 0.5. Okay. So how much it is? Let us try to find 1.25 divided by minus 0.5. So this is 1.25 divided by 0.5. This is 2.5 and it is minus 2.5, right? And then we take the tan inverse of this. So this is somewhere around minus 68 degree. Okay, minus 68 degree it is, right? Yeah, so this is somewhere around minus 68 degree, right? So 90 degree is a straight line, so obviously it looks like minus 68 degree, right?
Excuse me, sir.
In fact, it should not be minus 68 degree, it should be somewhere around minus 86.5 degree. So at minus 86.5 degree, you will find this dV out by dV in as minus 17, right?
Excuse
Since
me,
we did, yeah, please.
sir, the y2 minus y1 by x2 minus x1. X2 minus x1 is 0.05. You written 0.5. I think that's the mistake.
x2 minus x1. So x2
Y2
is
minus
1.25 minus 1.3. Yeah, it's 0.05, correct. So 0.05, yeah, correct. It is 0.05. So maybe let us make changes here. It's 0.05, correct. So I'll fix it to 0.05. So this is 0.05. So now it becomes maybe. Yeah, maybe. Yeah, correct. So, you do this, so it will come somewhere around minus 86.5 degree. Yeah? So this is not completely 90 degree. It will come somewhere around minus 86.5 degree. Right? So maybe I'll write here. So this is the slope of this line is minus 86.5 degree. Okay? That is dV out by dV in at this point is minus 17, yeah, which is plotted over here, minus 17. So this is minus 17 over here. Okay. Yeah, so that's how that way one can find out the slope of these lines on VTC, and also one can think about how to shift this switching threshold either towards VDD and ground by changing the sizes of PMOS and NMOS, or by making what we call as uh, a PMOS is strong or maybe a NMOS is strong. And now let us also talk about the role of supply voltage scaling. Okay. So we understand that through scaling, the device dimensions change. That is, the device dimension scale. Maybe they can be made bigger also, and smaller also. That is, W by L can be made smaller also, and W by L can be made bigger also. Right. So scaling of device dimensions, we understand. Now, when scaling of device dimensions are done, so at the same time, supply voltage scaling is also done. Yeah, so with device dimensions, supply voltage also scales. However, threshold voltage, it does not changes with scaling. It is kept constant. Okay. So what is the effect of this supply voltage scaling VDD? Okay. So the effect is that if you try to, let us say that the supply voltage is 2.5 volt here, and we draw the VTC at this 2.5 volt, and then let us say the supply voltage is reduced to 1.5 volt at this point. Now we see that at reduced supply voltage also, the inverter characteristic is still maintained. Yeah? Earlier the inverter characteristic was this. Now at reduced supply voltage at 1.5 volts also, the inverter characteristic is maintained. And even if we try to reduce the supply voltage and bring it near the threshold voltage of the MOSFET, right? So threshold voltage is, let's say, 0.4 volt, and we try to keep VDD or supply voltage as 0.5 volts. So then also we see that the CMOS inverter characteristic is maintained. Yeah, the circuit is still behaving like an inverter, right? So what is the reason behind this? I mean, at VDD of 0.5, which is very near to switching threshold, how can the circuit behave? Circuit work, or CMOS inverter characteristics are still maintained, right? So how is it possible? So the answer lies in the sub-threshold region of operation of the MOSFET. We discussed some time back that even if VGS is applied, and if VGS is less than threshold voltage also, still the MOSFET conducts. Okay? So that is called sub-threshold region of operation, and because of this sub-threshold region of operation, my inverter characteristics are still maintained. The current levels, of course, will be small. So the current level, that is current drive, will not be as good as this inverter, that is at VDD of 2.5 volt. But yes, the inverter characteristic is still maintained with a lower current drive. Okay. Now, if you try to further reduce this VDD, okay, from maybe 0.5 to, let's say, 0.2, even smaller than the threshold voltage of the MOSFET, right? So still my inverter characteristic is maintained. Okay. And in fact, in these three pictures, you will notice that the gain is improving, or what we call as the slope of this VTC line. So this is improving with supply voltage scaling. That is, when the VDD or supply voltage is scaled down, this VTC, that is this region, transient region, so this is becoming more straight. Okay, so that means the gain of this CMOS inverter is becoming good. Yeah, so from here to here and then here, it's becoming good. And if it is straight, then you might be knowing, we had studied that if it is straight, then the gain is infinity. Okay. So up to this point, the gain was improving, that is near switching threshold. Now below switching threshold, when VDD is scaled down below switching threshold, you will see that the curve which was getting straight here, it again started getting little bit tilted or slanted. So that means gain improvements were only possible up to this point, right? After that, if you try to reduce VDD, gain starts reducing, right? So gain is started to reduce here, and then if you further make it 0.1 volt VDD, it reduces further, and for 0.05, the gain of the entire transient region is 0.1, right? So earlier we had that at the border of this transient region, the gain was -1, but now when you reduce this VDD to this level, 0.05, still the inverter characteristic is maintained. One can say that still it is behaving like an inverter, but the gain of this transient region is reduced. Okay. Now because of this VDD scaling, that is, you are reducing the VDD, and we had understood earlier that the drain current ID, so that depends on VDD. So that means obviously the current drive or the switching current, what we call as, so that will be small. That is, current drive will be small. So that means my circuit will be slow. So the CMOS inverter will be slow because of lower current drive, because of lower VDDs, right? So reduce VDD, you reduce VDD, the circuit will become slow. The circuit will still perform like an inverter with reduced gain in the transient region and also reduced speed. Circuit will be slow, right? So now, but still you will find that these slow circuits, so they also will find some applications. So for example, they can be utilized in the digital watches, right? So digital watches, they do not need to be very high speed. So they work at a fixed operating frequency. So these such kind of circuits where VDD is small, very low, so they can be used in applications which do not require high speed performance. For example, digital watches or maybe calculators also, where you do not need very high speed. So there they can be utilized, they can be used. Okay. Now you will also find that because of very low current levels, okay, or when the VDD is scaled very down, that is entire circuit is operating at very low voltages. So inside the circuit at all nodes, the voltages are very small. Okay. Now at such small voltages, the nodes inside the CMOS inverter or any digital circuit can become sensitive to noise. That is, a small noise can even affect the voltages at these nodes, at the nodes of the internal nodes of the circuit. So circuit is more prone to noise in this case when VDD is very small. Circuit is more prone to noise, and also it is less robust. Okay, so that is one of the disadvantages of operating these CMOS circuits at low voltages. Okay. However, the power dissipation, obviously, you reduce this VDD, power dissipation will also be small, especially dynamic power dissipation, which depends upon this VDD, right? So it is in fact directly proportional to VDD. So you reduce VDD, the power dissipation can be brought down, but yes, the circuit will be more sensitive to noise now. So this question can come in your mind, that if my CMOS inverter can work at low voltages, and operating the circuit at low voltages has advantages like power dissipation is small, okay, then why not work at lower supply voltages only, and high gain is also possible at lower supply voltages. Yeah? So two advantages are there, that is, gain is high, power dissipation is also small. So why not operate our digital ICs at lower supply voltages, right? So the answer lies again when we look at the delay. So the delay will be more because the current drive is small now. The current flowing, that is drain current, is small. So TPHL and TPLH will go up, right? That is charging and discharging time. So that will increase. So delay will increase, okay, because of lower charging current and lower discharging currents or lower drain current because of the supply voltage scaling. And then you have also a possibility of sensitive DC characteristics. That is, now your VTC or DC characteristics, so they will depend now more on VTH, that is threshold voltage. And threshold voltage can change, because of numerous factors, right? We had seen the dependence of threshold voltage on many things, right? So, if threshold voltage somehow changes, then the characteristic of the circuit will also change. Now the other disadvantage would be that circuit will become more sensitive to noises, and hence it will also become less robust. Okay. So how much VDD is acceptable? Yeah. So then the question comes in mind, that how much VDD is acceptable, right? So VDD can be low, obviously, but how much low VDD is acceptable? Okay. So there is a rule that supply voltage, that is VDD, it should be at least a couple times KT by Q, 5T, thermal voltage. That is somewhere around 25 millivolts, right? So that is, it should be a couple of times larger than 25 millivolts. So normally it is said that 4 times it should be larger than this 5T. So that means 100 millivolt at least it should be. That is VDD should be at least 100 millivolts. Okay, to ensure that thermal noise does not become an issue, right? Because the system noise do not scale with VDD scaling, or maybe the device is scaling. System noise is still there. Of course, internal noises can be reduced, but system noise, that is external noise, they do not reduce. So they can affect the device performance also and circuit performance also, and then it can also result into an unreliable operation. Okay, so it is believed that VDD should be at least a couple of times 5T, that is at least 4 times, that is somewhere around 100 millivolts, so that circuit can work properly without any issues of thermal noises and these things, right? So noise should not dominate the performance of the circuit. To ensure that VDD should be at somewhere around 100 millivolts, right? Now somebody will still argue then that how to bring this VDD below 100 millivolts, right? So since phi t is kT by q, so if you want VDD to go below 100 millivolts, so that means you will have to reduce this T, that is temperature, ambient temperature. So if the ambient temperature can be reduced, then phi t can be reduced, right? So maybe from 25 millivolts, if you can reduce this temperature, maybe you can get 20 millivolts, right? So 4 times 20, that means VDD will be now 80 millivolts. Right? So that means to make VDD lesser than 4 phi t, one has to operate the CMOS inverters with a lower ambient temperature, okay? Or in other words, one has to cool the CMOS circuit. So you provide some sort of heat sink, good heat sink, which can cool down your circuit. The circuit can be cooled down, and obviously it can be operated below 100 millivolts. So that is possible. Now, one of the advantages of using CMOS ICs or CMOS circuits would be that these CMOS circuits are very much robust to the process variations. Right? So process variations, for example, we discussed that when you fabricate the IC, then in that IC, all the transistors, they will not have similar process parameters. Yeah, for example, in one of the transistors or maybe some of the transistors, you will see that oxide thickness is not same. Or maybe in some other transistors, you will see that the channel length is not same. Or maybe the channel width is not same. Though you try to keep all these parameters same, that is oxide thickness also you wanted to keep same, channel length and width also you wanted to keep same. But when finally the fabricated IC comes up in your hand, you find that because of these process parameter variations, the oxide thickness of all the MOSFETs are not same, length is also not same, width is also not same, and maybe threshold voltage is also not same. Okay, so these are called process variations, and the impact of these process variations is very minimum on the CMOS circuit performance. Yeah? So that is one of the advantage. Okay, so for example, here a simulation has been shown where this red line, the red VTC. So this corresponds to the case when my PMOS is good and NMOS is bad. Okay? So I say my PMOS is good by observing the oxide thickness. So if my oxide thickness is less than 3 nanometers, right? I mean lesser by 3 nanometers. So I say that this is good oxide thickness. Or maybe channel length is smaller by 25 nanometers. I say it's a good channel length. Or maybe the channel width is plus 30 nanometers or 30 nanometers larger. So I say it's wider MOSFETs are good, better. So we say that these are the parameters of my good device. That is oxide thickness, if it can be smaller by 3 nanometers maybe. Channel length, if it is small by maybe let's say 25 nanometer. Channel width is larger by 30 nanometer, and threshold voltage is also smaller by 60 millivolts. So I say that this is my good MOSFET. Okay, so this case is, that is red one, this one. So this is for the scenario where my PMOS is good and NMOS is bad, right? So just opposite of this, you apply to NMOS. Okay? So that means my NMOS will become bad. Okay? Now this case, blue one, right? So this is for when the NMOS is good and PMOS is bad. So the VTC, there is very minimum or minimal changes, right? Though there is some shifting from center to right when I have a good PMOS. So obviously it will be. We had discussed that since we want the VM to go up, so VM can be seen here. It's going up when I have a good PMOS, right? So good PMOS has wider channel width. So obviously with wider channel width of PMOS, my VM will be larger, right? So VM is larger here compared to this one and also compared to this one. So I have to bring down my VM. So I'll make my NMOS good. That is, I'll try to increase the width of my NMOS by, let's say again 30 nanometer. Okay? So my VM, that is switching threshold, that can be brought down here. But yes, these changes are very minimal. That is, impact of process variations on the CMOS inverter characteristic is very minimal. That is, the circuit is more robust. So that is one of the advantages of using CMOS circuits. Okay, I think these things we have seen, so I'll not go into this. And now let us come on to this propagation delay. So for propagation delay calculation, there could be two approaches. First approach could be that you replace your, maybe let's say we are trying to calculate TPHL, high to low, via this NMOS. So NMOS is replaced by this current source, right? Average current. Okay. So then you apply this I is CdV by dt, and you bring T over here. So by this you can find out the high to low time. Okay. So we swing by 2 here has been done, maybe because we are interested in 50% time. So let's say 50% of the output. So we swing by 2 we have included. Okay. So that way one can calculate the propagation delay. And the other approach that we had studied, that is by utilizing the on resistance of NMOS. Okay. And then applying this delay for this lumped line, that is 0.69 R on CL. Again 50% delay we are talking about, 50% point. Okay. So these two would be the approaches. That is, first approach is replace the NMOS by its current. Okay. And the second one is replace the NMOS by its on resistance, and then find TPHL by using the delay equation for the lumped first order RC circuit, that is 0.69 R on CL at 50% point. Now if you do this transient response to find out delay, so one can calculate delay as the average of TPLH and TPHL. Okay. Or you replace TPLH and TPHL by this R equivalency RC. Okay. For LH, low to high, you have PMOS coming into picture, and for HL, that is high to low, NMOS is coming into picture. Resistance of NMOS is coming into picture. Okay. Now here in this transient response, you would be noting these 2 points right here. So these are called overshoots and undershoots, and these are because of the gate to drain capacitance. Okay. So because of the gate to drain capacitance, okay, which is appearing here, maybe the gate to drain capacitance. Okay. So because of this gate to drain capacitance, input which is applied here in the CMOS inverter, of course we have a PMOS also over here above this. Okay. So because of this gate to drain capacitance, whatever input is applied, that input can appear at output even before my transistors respond to this input. Okay. So even before the transistors are on or off, this input can be connected to the output. So because of this gate to drain capacitance, we see a spike in the output. Okay. And the result of these two spikes are that the delay further increases. Okay. So delay of my CMOS inverter will further increase, and this R equivalent N and P can be calculated by the same old formula, okay, which we had seen earlier. So equivalent on resistance of NMOS and PMOS can be calculated by using this formula. Okay. Yeah, so CGD, so that couples input to output even before transistor is on. So because of this, overshoots and undershoots can be seen, and because of these overshoots and undershoots, you will see that the delay of this CMOS inverter also increases. Okay. Now the delay versus VDD. So we had earlier commented that when you increase VDD, the delay goes down, and when you reduce VDD, the delay increases. Okay, so that can also be seen over here. In fact, it can be found by again using the same equation which we saw here, that is the delay equation for TPHL. Okay, so for TPHL we had this delay equation 0.693/4 CL VDD by ID sat n, right, and replace ID sat n, that is saturation current, by saturation current over here, and then you see that VDD term is appearing in the denominator also and numerator also. Okay, so from here one can say that when you increase VDD, okay, so when you increase VDD, maybe the delay can be brought down. So when you increase VDD, the delay is brought down. So you see that when VDD is increasing, this is delay here, normalized values are there. Okay. So the delay is coming down when you are increasing VDD. Simply just try to increase VDD over here. You will see this TPHL value will come down. Okay. Now, in majority of the designs, you will see that VDD is chosen large. Okay, so this VDD is chosen large in majority of the designs. So how much large? VDD is kept very much greater than VTN plus VD sat n by 2. So this term is appearing over here. So if you keep VDD very much larger than this term, so that means the delay equation, that is TPHL, will have no role of VDD now, right? So that can be seen over here, maybe somewhere here 2.2 to 2.4 volts, where increasing VDD has no more effect of reducing delay, right? So delay is now becoming insensitive to rise in VDD or changes in VDD or increase in VDD. Okay. Yeah, so TPHL modifies. Okay, so if you keep VDD much larger than VTN plus VD sat n by 2, which is appearing over here, so the total delay, that is high to low delay, so that becomes independent of this VDD. Okay, so that means maybe somewhere around this point you see that VDD, increasing VDD has almost negligible change over the delay. Yeah, but yes, one has to also notice here that when you reduce VDD, right, so when VDD is scaled down, so somewhere at this point, okay, that is maybe a 0.4 voltage if the VT of the transistor, so that means 2 VT points, okay, 2 threshold volt, 2 VTH points, so that is this point here. So at around 2 VTH, VDD is equal to 2 VTH, there is a sharp increase in the delay. Okay. So the delay increment is very sharp as the VDD is scaled down and it reaches somewhere around this 2 VTH value. Okay. So this gives us another guideline that never try to reduce VDD below this 2 VTH or around 2 VTH. Do not keep it in this range, maybe in this range also, one can say. In this range, don't keep, otherwise the delay will start increasing, right? So though you have of course got some advantages in terms of power dissipation, which is small, but that advantages nullified or dominated by the increase in delay, right? So it is of no point to keep VDD near this 2 VTH value, yeah, because increase in delay is too high. So this region should be avoided. So some guidelines for designing integrated circuit with very high performance. Yeah? For high performance integrated circuit, so these are some of the guidelines, okay, based on our discussion that we have done so far. So number one is keep capacitances small. Okay? So keep capacitances small, that means internal capacitances, that is drain diffusion capacitances and the source diffusion capacitances. So keep them small, or maybe also wire capacitances. So how to keep these capacitances small? Good layout practices. That is, if you are very careful at the layout, one can bring down the drain diffusion capacitances. That is, if the drain diffusion areas are small, okay, so that can also only be small if you are careful at the layout. So try to make drain diffusion area as minimum as possible, as small as possible, so that the capacitance is also small. Okay. Hence, small intrinsic capacitances can result. Then the next rule for designing for high performance is increase the transistor sizes, that is W by L ratio. So L we don't change, okay, but W we change, right? Because process technology, L is constant. Maybe if we are working on 0.25 micron process, so L will be always constant. So, but yes, W can be varied. In fact, this is the only tool in the hands of the designer. Okay, that is W. Okay. So W can be increased. So when you increase W, we had seen that the resistance of the MOSFET can be brought down. Okay. But then with the reduction in resistance, you will also see that the internal capacitance of the MOSFET also go up. Okay. So you have to keep optimum width of your MOSFET, where this self-loading effect, that is MOSFET is loading itself because the intrinsic capacitance is now greater than the load capacitance. Okay. So that can happen, that can scenario can happen if W is kept very large. Okay. So that sets another guideline on minimum or maximum W that is possible, right? That is optimum W at which the self-loading effects do not come into picture. That is, MOSFET is loading itself, okay, because the load which is connected, the capacitance of that load is smaller than the intrinsic capacitance, because transistor sizes we are trying to keep big so that resistance can be brought down, so that the delay can be brought down. Now we also saw that one can think about increasing VDD to bring this delay down, right? So increasing VDD makes the delay small. Okay, but then how much VDD has to be more, right? How much high VDD you can keep. Okay, so that will again require some sort of investigations and thought and thinking that we had seen some time back when we were talking about devices, that if you increase this VGS, then the electric field, transverse electric field, that is gate to bulk electric field, so that becomes very high, and because of hot electrons or hot electron effects, the electron can tunnel through the oxide and enter the gate region, okay, which is also called oxide breakdown. Okay, so which is only possible when you're increasing VDD above some certain level. So one has to keep in mind about these two effects when increasing VDD. So that means there is some optimum value of VDD also, below, above which VDD should not be raised. Okay. And then also we understand that if you increase VDD, then power dissipation also goes up. Okay. So one has to increase VDD so as the power, so as to keep the power dissipation and delay both minimum. That is, there must be some trade-off between power and speed, or maybe trade-off between what we call as energy and performance. Okay. So these are some of the rules which one can follow while designing the digital integrated circuits. Okay. Now you will also see that when you are sizing the device or scaling the device. Okay. So let us say we have a scaling factor of S. Okay. So let's say that we are increasing the size of the MOSFETs by this scaling factor. So if I say that S is 2, that is scaling factor is 2, so that means my MOSFET is now double or twice the size of my reference MOSFET, right? So some let's say if the reference MOSFET PMOS has the size of WP, then if I apply S scaling factor of 2, so the total size now becomes 2WP, okay, double. Okay. Now with this scaling up the device weight, we had seen that the intrinsic capacitance and resistance, they also scale. Okay. So we had seen that the resistance of the MOSFET comes down if you increase the width of the MOSFET, right? So how much it scales down, you divide it by the scaling factor. Similarly, intrinsic capacitance, they scale up. Okay. So how much, you multiply it with the scaling factor. Okay. So we normally try to keep wider PMOS in a CMOS integrated circuit. Yeah, in a CMOS circuit, we always try to keep PMOS wider. So why do we do this? So that the resistance of NMOS and PMOS can be same, right? Because my PMOSs are smaller, PMOSs are slower because of the mobility of hole is small. We say that PMOS is slow. So to make my PMOS fast, okay, so we can bring down the delay of the resistance of this PMOS. So if you reduce the resistance of this PMOS, then TPLH, so that can be made equal to TPHL. Okay, so that you will find symmetrical VTC. So VTC, for making VTC symmetrical or for making TPLH is equal to TPHL, or for making the resistance of the pull-up network equal to pull-down network, you can think of increasing the width of PMOS. Okay, and because of symmetrical VTC, you will also find that noise margins also improve. So we had some time back commented on this, that is, the noise margin depends on your VTC. Okay, so if VTC is symmetrical, the noise margin will be very high. And we also find that delay can be smaller if PMOS is small, right? Yeah, so apart from this, that is equalizing TPLH and TPHL by making PMOS wide, one can also argue that delay can be smaller if PMOS is small. Okay, so how the delay can be smaller? Okay, so the delay can be smaller if my PMOS is small, because my drain diffusion resistance. Okay, so that can be brought down. Okay, so TPLH can be also brought down, right? So though in this step we are making PMOS wide, so obviously we are trying to increase the current driving capability of PMOS by making it wider, so that the load capacitance can be charged faster. That is, TPLH is obviously brought down here, no doubt, but TPHL is degrading because size of the capacitor is increasing at the output, right? So because of that, the same NMOS has to now discharge a higher capacitance value. Okay? So TPHL degrades because of increase in width of PMOS. But yes, TPLH reduces. So TPLH reduces, but TPLH reduces, but TPHL goes up because CL goes up when you increase the width of your PMOS, right? So these are few observations one can make out, and you will see that when you increase the size, okay, so the delay can be brought down obviously. So we see that when you are increasing the size of PMOS, the delay is coming down. Okay, but now at this point maybe, okay, from here to here, okay, we see that the delay is not improving. Okay, so this is the point where my self-loading effects are coming into picture. That is, now here at this point, in this region, the intrinsic capacitances of the MOSFETs are now dominating the load capacitance. Okay? So because you are increasing the size of PMOS, so obviously the drain diffusion capacitance associated with PMOS is increasing. So the total drain diffusion capacitance is also increasing. So in fact, the CMOS inverter is now self-loading itself. Okay? So this is a problem here. In fact, you should not increase the size of PMOS beyond this range. Okay? And beyond this range, you will see that very slow further improvements in delay are seen. Okay, and it is also not economical to increase the size of PMOS beyond this point, because increasing the transistor size also requires you to utilize more silicon area, right? So more silicon area is required now. Okay, and also it is not economical because the delay is not improved further. Very slow further improvement in delay are seen. Okay, however, the size required is now more, silicon area is more, so it is not advised to scale up your PMOS beyond this limit. So that means there must be some optimum NMOS to PMOS ratio. Then how to derive this optimum size ratio? So that is also a important concern. So this thing we will see in the next class, how to derive the optimum size, okay, of CMOS inverter, the devices in the CMOS inverter. But yes, from here, this plot where this beta is again the sizing factor, okay, and you will see that when you increase the size of your PMOS, okay, so when you increase the size of PMOS, so PMOS is more strong now, right? So if I increase PMOS size, so PMOS is more strong, so that means current drive of PMOS, so that also increases. Okay, so current drive of PMOS also goes up, so that means TPLH, so that will also come down because my current drive is now increasing, so I can quickly charge the load capacitor. So that is why we see that when WP is increasing, TPLH is coming down. So that can be seen here, right? So this is TPLH curve, this one. So we see that when WP, that is size of MOSFET, is increasing, TPLH is coming down, okay? Because the current drive capability of PMOS is increasing, so the load capacitor can be charged more faster. Okay? But yes, on the other hand, you will see that the load capacitance, that is intrinsic capacitance, let us call it. So intrinsic capacitance of, that is the drain diffusion capacitance, so that starts going up. Okay, so that means beyond this point, it TPHL starts going up, because the intrinsic capacitance, that is total load capacitance, that also goes up. So now more would be the TPHL, that is time to charge this capacitor. Okay, so that is how you see that the TPHL, this has started increasing with increase in the size of PMOS. So the total delay, so that also starts increasing beyond this point, right? So now where these all three curves meet, so we can say that this may be my optimum WP. That is, I should not raise my WP above this. Okay. So at this point also you will notice that TPLH and TPHL both are same. So that my VTC will also be symmetrical. So high noise margins are possible. Though the delay you will find, so that is, you know, smaller, maybe somewhere at this point. Okay. So the delay is smallest at this point. Okay. The delay is small here compared to this point, this one. Okay. So when the delay is more important, you will try to use, a PMOS width of this much. And if noise margin is more important, one can size the PMOS up to this point. Yeah, so two guidelines are again presented here. So maybe I'll stop here, and then we will try to see in the next lecture how to size the inverters, or how to size any digital IC circuit to so optimum sizing we will discuss in the next lecture. So let us end the class here itself, and if you have any question, then maybe you can ask.
Hello, sir.
Yeah, please.
Sir, in the case of sub-threshold region, we cannot drive the another circuit with the help of so much low current and the voltage at the output of the inverter. Then what is the fun to use it? Actually, there is no circuit in which alone CMOS or alone CMOS, not alone inverter is used.
Yeah, so you can try this. So no issues. So that can be tried.
Okay.
Right. That can be tried. But yes, the circuit will be, very slow. So it may not be of any use, except few applications. For example, as I told you, digital clocks or watches, and then calculators. Yeah, anything else?
Sir, if VDD is less than VTH also, CMOS inverter works, sir.
Can you please repeat your question, and can you please speak louder?
If VDD is less than VTH, we reduce VDD.
Okay.
Then also the CMOS inverter circuit works as it is, like the voltage transfer characteristics will be as it is, as usual it is.
Yeah, correct. So characteristics are still there. I mean, the inverter characteristics are still seen at VDD even below the threshold voltage. So that is because of the sub-threshold region of operation of the MOSFET. So that is how you are seeing still some current at the output. So that is why the CMOS inverter is still behaving like an inverter. But yes, the current drive, that is current that is obtained, is very small. The value is very low, very small. So the circuit is very slow because of this. Because charging and discharging depends on the current drive. So the circuits become very slow.
Sir, and VDD also, you said we have to give 100 millivolts like that.
Yeah, so how much lower VDD is possible? Yeah, we saw that even at 0.1 volt and even at 0.05 volts, CMOS inverter characteristics were still shown, right? So how much VDD, should be scaled down so that the circuit is free from any noises. So any, noises, thermal noise especially, or maybe system noise, so that it does not affect the performance of your inverter. So that guideline or recommendation is that the VDD should be at least a couple of times 5T, that is somewhere around 100 millivolts it should be. And if you want to, couple of times means 4 times, somewhere around 4 times, or maybe 5 times or 6 times, right?
Okay,
So it's, yeah. So even you can bring it down if you can, you know, reduce the temperature of the surroundings, or maybe if you can provide a very good heat sink so that the circuit can be cooled down. So then the VDD can be further brought down.
Okay, sir.
Yeah. Anything else?
Excuse me, sir.
Yeah, please.
Sir, in that VDD scaling case, suppose we are decreasing the VDD, we are getting the better transfer characteristics similar to the ideal first case, and further we increases the VDD. VTC is it's like not very disturbed kind of thing. Why it happens? Earlier VTC is similar to the ideal case, and then it is not. Why?
Yeah, so there has to be some limit. I mean, you are operating it at in the sub-threshold region. Okay. So in the sub-threshold region, there is some limit. After that, the gain of the circuit starts falling down, right? So there is some limit. I mean, it is not desirable to operate the CMOS inverters below threshold voltage. Yeah, the devices below threshold voltage, because you are not expecting any current, but still the circuit is behaving, right? So you don't want to operate. Okay, so it is actually undesirable. So we don't want it, but still it happens. It operates. So for low power, for low power applications, so this can be used. Okay, that is sub-threshold region of operation. But still, we are not sure that what will be the actual value of the the current levels when the actual fabricated circuit comes up in our hands, right? So it is undesirable. Yeah, it is undesirable. Yeah, anything else? So I think Sonal, you have asked that is this concept used in low power IC design? So yes, it is used in low power IC design, that is supply voltage scaling, and also threshold voltage scaling. You will find multi VT and multi VDD, multiple VDD. So this is used in low power IC design. Yeah, anything else? Yeah, so if you don't have any questions, then let us end the meeting here itself. Okay. So we'll meet tomorrow. So I have to cover